Over the years of my teaching career, I must have taught a class of thousands of Year 10 and 11 students, and some of them were very bright and capable physicists, but not once was I ever asked, hold on sir, how come the nucleus with these positive things packed close together doesn't just go bang? Good question, and that's the subject of this video.
Imagine two protons, which of course we know are both positive. We're going to consider the forces acting on these protons as we try to bring them closer together. By convention, we say that repulsive forces are positive. There is an electrostatic repulsive force between these two protons then. If you've had the joy of doing electric fields in Year 13, you'll know that this follows a 1/r² pattern. Don't worry if that didn't mean anything to you, it soon will. But for now, just accept the fact that the force that is repulsive between these two protons grows large rapidly. We can show this graphically. As one proton approaches its stationary friend, you can see this in the green curve. Notice how quickly the green curve rises. Considering how small the mass of a proton is, this repulsive force between these two protons is truly enormous. The diameter of a proton is around about, give or take, roughly, to a good approximation, 10 to the minus 15 metres. Now we call 10 to the minus 15 a femto, and this is easy to remember because both the femto and 15 begin with an F. This point here on the x-axis is showing a distance of 3 femtometers then, which is roughly about 3 proton diameters. Notice all the hand waving that's going on here. We're not really interested in exact measurements, but approximations are going to be fine for us. Given how large this repulsive force is between these protons, we can see that we've got a bit of a problem developing here. How can a nucleus stay together? Surely the protons should just literally blow each other apart. In order to put a lid on the potential problem of the exploding nucleuses, there must be another force at play. Clearly this is the case because, well, we just wouldn't be here, would we? So, enter the strong nuclear force. The nature of the strong nuclear force is quite different to any other force that you've met. For starters, it's a short-range force. Let's picture the moving proton coming closer to its stationary friend. At large distances, whatever that means, there simply is no strong nuclear force. There will, however, still be some electrostatic repulsion. As we move closer, we find at around about 4 or 5 femtometers, the strong nuclear force is beginning to slowly increase. But overall, there is still a larger repulsive force between the protons. Moving closer still and arriving at around 3 femtometers, we see that the strong nuclear force starts to increase rapidly in magnitude, peaking at a separation of around 1.5 femtometers. Notice though that the strong nuclear force is negative, which according to our convention means that it is an attractive force. Therefore you can see that at around about 1.5 femtometers, the resultant force between the particles is now strongly attractive. As we go even closer, the strong nuclear force begins to become rapidly less attractive, and at around half a femtometer flips over to being repulsive and continuing to increase rapidly as you get closer. Like I said, the electrostatic force and gravitational force are nothing like the strong nuclear force. So you can see that if you try and push two protons closer than, well, shall we say, I don't know, 1 femtometer, very quickly the force is going to become extremely repulsive. In other words, you can't get them closer than that. And there is a sweet spot round about 1.5 femtometers. One other important point is that the strong nuclear force applies to all hadrons, and naturally that includes neutrons. And so a proton and a neutron will feel the strong nuclear force if they get close enough, as indeed will two neutrons.
The neutron is often described as the glue that holds the nucleus together. Let's see if we can see why. I want us to imagine a slice, one row, through a relatively large nucleus. We're going to go proton, neutron, alternately, just to keep it simple. Let's pick any two particles that are separated, well, any two particles that are adjacent to each other. Obviously, we have one proton, one neutron, so there's going to be a strong attractive force between those because their distance between their centres is going to be around about 1 to 1.5 femtometers. However, there'll be no repulsive force because one of them is neutral, therefore strongly held together. What if we take alternate protons? So we go proton, neutron, proton. Well, in this case, we have two positive particles separated a distance of around about 2 to 2.5 femtometers. And as I'm sure you can see from the graphs earlier, the strong force is beginning to fall off a bit at this point. But we also now have a repulsive force caused by the fact that they are both positively charged. So now it's getting a bit more complex. We're going to have to look for a resultant force. Probably between those two protons is going to overall be attractive. But what happens now if we move out to two protons separated by, let's say, around about 4 to 5 femtometers? Now in this case, the strong force has fallen away basically down to 0, but there is still a repulsive force between those particles because, well, as we know, electrostatic force is not a short-range force. Although we are still firmly in hand-waving territory, I think you can begin to see that the neutrons are acting like glue since they attract all of their nearby neighbours without experiencing any repulsive force.